Okay, geometry fans, we are going to take a look here at the same notes that we started yesterday. At the top it says Notes 10-4, Chords and Tangents. Now we did the front yesterday, we talked about chords. Today we're going to talk about tangents, which is on the back. So go ahead and flip it over to the back side. And before we start, let me tell you your geometry joke of the day. And the question is, why did the obtuse angle go to the beach? And the answer, because it was over 90 degrees. All right, so after you're done laughing at that, let's take a look at this first theorem here. It says if a line is tangent to the circle, then it is perpendicular to the radius drawn to the point of tangency. Now, in this case, we don't need to have a perfect circle, but let's go ahead, let's use the compass, and let's draw one anyway. Doesn't need to be very big. All right, so there's the circle. If we have a line that is tangent, now tangent means that it intersects the circle but only in one place. A secant hits the circle in two places and creates a chord. So a tangent is only going to touch the circle at one point. And that point, we'll say, is right there. Now, the name of that point, we say that is a point of tangency. Point of tangency. That is where the tangent hits the circle, only at that one point. Now, if we connect that to the center, we just created a radius. And if you eyeball this, what would you guess about the relationship, the angle measure that gets created by the radius and the tangent? Now, it certainly looks like 90 degrees, and as a matter of fact, it is 90 degrees. That's always going to be true. Now, anytime you have 90, you can somehow, if you connected this in a way, now you have a right triangle. And so you can start thinking a squared plus b squared equals c squared. So a radius or a diameter is always perpendicular to the tangent at the point of tangency. So let's look at a couple examples. Number 4. It says find AB, and this is the circle with the center at A. So here's 6, here's 8. Now the other thing is we have to assume, let's assume in this case that this is a tangent right here. So that means this is 90 degrees. And if that's 90, and if you want AB, that's this whole thing, let's just call that x. That would be the hypotenuse because it's opposite the 90 degree angle. So we've got A and B are 6 and 8, those are the legs. 6 squared plus 8 squared is x squared. One thing you notice, we're getting the same values quite often. 6, 8 is very popular in right triangles, that adds up to 100. And when you solve that, take the square root of both sides, 10 is equal to x. Okay, so your answer is going to be 10. That's the length of AB. Number 5, circle with the center at P. Find x. All right, again, x is a tangent, so that's a right angle. Now, 9 is a leg, x is a leg. This whole thing is the hypotenuse, but it's not 6. 6 is just this outside piece right here. Well, so how do we find the hypotenuse? What would be this length here? Well, if you look at the picture, this is a radius. And this is a radius, the 9. Radii have to be the same in a circle. So if that's 9, then this is 9. That means the whole thing is 9 plus 6, which is 15. So again, we can do Pythagorean theorem. X and 9 are the legs. X squared plus 9 squared is 15 squared. That's x squared plus 81 equals 225. Now we solve it. We subtract 81 from both sides. We get x squared equals 144. Take the square root of both sides. X equals 12. There's your answer. So that's number 4. That's number 5. So just like yesterday, you will have right angle measurements. You have perpendicular relationships when you're talking about circles and tangents and chords. And when you have that, you have right triangles. Okay, Pythagorean theorem. The second theorem here, we're going to create another circle. And this one is going to be, this is important that we have a good circle, because we're going to measure this and we're going to come up with our relationship. And here's what we're going to do. We're going to pick a point outside the circle in the exterior. Let's just call that A. Okay, there's a point outside the circle. We're going to draw two tangents from A to the circle. Now a tangent only hits a circle in one place. Okay, so we're going to take A and we're going to draw a line. Let me try that again here, make it a little bit more accurate. Okay, here's the point of tangency. Let's call that B. There's the point of tangency. Let's draw a second tangent from A. We'll draw it down here. And this point of tangency, we'll call that C. Now, if you had to guess, what do you think's true about these two segment lengths? Well, let's go ahead and measure with the ruler. So the length of BA for me is about 3. It's about 3 centimeters. The length of CA is also 3. So what happens here, these are both the same. They're congruent. And here's what the theorem says. If two segments from the same exterior point are tangent to a circle, then they are congruent. So segment AB is congruent to segment AC. That's always true if the two tangents are from the same outside point. And exterior means outside. So let's look at example number 6. It says find x, circle with the center at P. Now, this is a quadrilateral here. You have 3 right angles, which means this is also 90 because they have to add up to 360. That's a rectangle. And in a rectangle, you know the opposite sides are congruent. So this is also x. Now that doesn't really help us. But if you look at the left side and the right side is 8. That means the left side is also 8. Now what that also tells us is that we can find this piece right here. We can do 8 minus 2 to get what's left over, which is 6. Well, x is a radius. 6 is a radius. So that means these have to be the same because the radii are always congruent. X equals 6. And then the last problem here. Now we did number 8 yesterday. Okay, so for number 7, wow, that looks complicated, that picture. Triangle TRW is circumscribed about the circle with the center at A. Circumscribed means that the figure is outside the circle, but it's touching, the sides touch the circle. Inscribed is inside the circle. Circumscribed is outside. If the perimeter of triangle TRW is 42, MR is 6, there's MR, let's label this, WM is 7, find the length of TR. We want to find the length of TR. Now, if we start with 6, that's RM. Notice that R is outside the circle. Let's assume, if this is circumscribed, then all of these are tangents. So if RM is 6, RL has to be congruent, so that's 6. Two tangents from the same exterior point have to be congruent. So what does that say about KW? Then that would have to be 7. Now, the last two segments here, TK and TL, those have to be congruent because they're both from point T. So how do we find it? Well, we have to use the other piece of information. Triangle TRW is 42, the perimeter. Now, if we add these up, 6, 6, 7, and 7, we get 26. Now, that's not the answer. We're still missing these two sides. All right, let's call them x and x. If I take 26 plus x, which is 2x, that gives me perimeter, which is 42. Now we can solve this, go minus 26 minus 26. We get 2x equals 16. Divide by 2, and x equals 8. And that is the length. Well, let's see. Oh, that's not the length. The answer, it says find TR. Well, if this is 8, the whole thing is 8 plus 6, so TR is 14. And that is the end of notes.